from the graphs and the reading that you guys did alongside of me, some of the questions. How did you guys feel about part 2 compared to part 1 of the web quest? Well, it was definitely much harder. Like, I totally get that. But do you know what equilibrium is? Say again? Yeah? No? Okay. Does anybody want to just give me your own personal definition of what you think equilibrium means? Syrian.
Like chemicals, just how like whatever happens to one side has to the other, so it has a constant balance each other.
So like if some reactants react, so this is kind of like the goal here. So as reactants react, they don't just disappear. What do they form? Products. And as products themselves react together, they don't just go nowhere. What do they reform? Reactants. So this constant back and forth, back and forth, back and forth. So we call the forward reaction the forward reaction, and we call the opposite of that the reverse reaction. So we're basically talking about these reactions that can go both ways. Who in the lab we did with the purple colored solution saw the very, very, very final trial? It took forever to turn, right? Okay, so forever, like 12 seconds to turn. But did it kind of like have this hint of white and purple still together? Did it turn 100% black to purple? Do you remember? Some people, when they swirled it, it went back to whitish clear. So it actually reversed itself. So there are a lot of reactions that can do that. So that is what equilibrium is. Give me some more. What else did you guys kind of just hear or learn about equilibrium? Or how do we express something about it? Something other than Syrian? Meredith table back there? That whole section can tell me something? Yeah, Avery. What about the rates of the forward and reverse? They have to be the same, right? So we're going to do some graphing real fast, and that will help you like interpret if a reaction's at equilibrium or not. So you guys drew a couple of graphs as you were supposed to on part 1 or A of part 2. So right here under this section, I'm trying to consolidate all the most important pieces of generic information about equilibrium and sequentially more specific information regarding different types of reactions that we have. So I'm going to try to hit these through a couple of notes. So you guys have this pulled up, right? So I'm taking this down. So this is under homework. It's the very last thing on the homework side. All right, so whenever you're looking at equilibrium, you are talking about rate. We already know a little bit about rate. Just like when you travel to school, rate is a distance per time, so like 35 miles per hour. But in chemistry, you don't really travel distances, right? They're in a test tube. We're looking at reactants and we're looking at products. So what we actually measure is not distance, we measure amount. So when we measure amount, we're looking at the quantity of reactants or quantities of products. Sometimes they're colorful, so like in that lab we did, we have this clear solution, this blurry solution, we put it together, and then what color happened? Blackish purple. Well, that was the product made. So we look for the appearance of that product because we visually see it. Not all the time can we visually see those products because they're just not all colorful. Many times it's like a transition metal that would be present. But we can measure that. We can measure it over the course of some time, and that's what we call rate. So when you're talking about rate, you can always imagine it's some change over time. So when you have a graph related to that, it's many times graphed as concentration versus time. So your axes for a rate or an equilibrium graph would be something like this. You would have concentration on the y-axis, time on the x-axis, because the time is kind of your independent variable you're allowing it to run, and you're looking for the changes of course of either the reactants or the products as time progresses. So for a reactant like the clear solution A plus B, we made that black colored iodine solution. You could visually see the block forming over the course of the reaction. So before the reaction occurred, before you added these two things together, how many products did you have? Say again? None, right? So on a graph, I'm going to kind of keep this right here, showing you this one right here, the purple one, the product one. So at time 0, you have 0 concentration of products. At time 0, you had, in this graph in particular, you had 0.1 molar concentration of said reactants. So over the course of the reaction, what happens to the reactant's concentration? Why is the reactants, so assuming we're starting with all these reactants, we're starting with 0.01 molar, why do they go down over the course of the reaction? There's a law of conservation of matter. I'm hearing that. Keep going. They react and they form products. Like you can't just form something from nothing. So the reactants had to be consumed, taking them away, forming products, but due to the law of conservation of matter or mass. So as these go down, what starts to happen to the products? they're going up. Okay, and as the reactants continue to get consumed, they're decreasing in concentration, and the products are increasing in concentration. And we can keep going and going and going until eventually, so the reactants reacting, which is the what type of reaction? Is that the forward or the reverse? Forward. Okay, so we're allowing the reactants to react. They're moving in the forward direction. We're eventually, allowing these products to form. They're forming. They're forming. They're forming. Oops. There's the red right there. Okay, they're forming. They're forming. They're forming. Eventually, these reactants start to. Do you notice the slope is changing? So the reaction rate is super fast, slowing, 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 and eventually it slows down to the point where the slopes are now becoming equal. Do you see that? Okay, so what does this slope represent? What does slope in general represent? Yeah. When they're equal, it represents equilibrium, but I want you to use the right word to kind of what Avery was saying about. Tell me first, what does this slope represent? Just like any slope in any curve whatsoever. So if I want you to calculate slope from here to here, what would you do? So you said y what? y2 minus over x2. Okay, so basically you're looking for change in y over change in x, right? Well, what's y's axis? Concentration. What's x-axis? Time. So what's concentration change over time? Rate. Okay, so that's rate. So we basically are saying the slope is rate. Okay, what eventually is starting to happen to these rates? They're not changing. Avery, what did you say the definition of equilibrium was? Rate of the forward equals the rate of the reverse. Okay, the rate of the forward equals the rate of the reverse, and they are going to be staying the same because at this point we have basically met the point when there's no net change overall. Now this reaction is still making products and making reactants, making products and making reactants, but at this point in time there's no overall change. You're not seeing a change. It's still dynamic equilibrium. Things are still happening. But what is the slope here? 0. What's the slope here? 0. So you can definitely tell mathematically they are also equal. But when the rate of the forward reaction equals the rate of reverse reaction, we are at equilibrium. So you can tell me what time, according to my graph, we met equilibrium. What time do we need it? About what? My graph's a little wonky, but yeah, about 250, 260 seconds, I met equilibrium. Up here, I wasn't at equilibrium because the rates were still changing. The reactants were still decreasing in concentration. The products were still increasing in concentration. Well, then we crossed lines, but they're still changing, they're still changing, they're still changing. Now we're at equilibrium. That is what an equilibrium graph looks like from here over. Okay? So what's interesting here is what you can now talk about is what's favored at equilibrium. Are the products favored or are the reactants favored at equilibrium? Favored just means more or higher concentration. Who has a higher concentration at equilibrium? Products or reactants? How do you know? Because the line's high and the reactants line is low. That's it. You're looking at the products concentration is like 0.1. Reactant concentration is getting close to 0. So who's favored? Products are favored. So you can graphically see it. You can also mathematically see it in a K expression. So, speaking of that K expression, what is a K? So, sorry, let me tell you what a K is. K is called the equilibrium constant, and it is a value. And that value is going to tell you something about the favorability of the forward reaction. So, it'll tell you the extent of the forward reaction. So you guys wrote down your K expression, the generic form, the most generic form you could achieve from a basic reaction, something like A plus B equilibrates to C plus D. Reversible arrows like that, we could just say equilibrates because we're assuming it's going to be eventually going to equilibrium. So with these being your reactants and products, we put like little a's, b's, c's, and d's to represent their coefficients. Ashton, how did you write your expression? for K using this generic form. Which section was that under? It's like 1 or 2. Say again? Some of them were examples and some of them were the generic form. It's under the reading part of A. Yeah, Zach.
Wait, are you still asking?
Yeah, but I'm hoping somebody can tell me. You got me? Tell me how to set this up. Say again. Concentration of C, so that's product C times concentration of product D. Both of those are raised to their coefficients as a power. So these little coefficients right here, C and D, those coefficients become exponents, C and D. So that does matter, that is balanced. And that's over what, keep on, Zach? To the A power, okay. Beautiful. So this is a really generic form of this. These A's and B's are this A right here and this B right here. And we're just assuming that everything in this reaction right here is qualified to go into a concentration in terms of equilibrium expression, what you can put in there. So this is what you throw in there. But what you're basically saying is this is a ratio, this K value represents a ratio of products over reactants. That's it. Products over reactants. And of course, concentration brackets mean molarity, so I'm just, again, plugging those in. Just jump right in, okay, Megan? So with that knowledge, you now should be able to tell me that graph that I had earlier, who was in favor again? Products or reactants? Products. So you guys said the concentration of the products was higher, right? Okay, when I plug in numbers here, it doesn't matter what they are, but when I plug in a number that's higher on the top, because the products had a higher concentration, than a number on the bottom, what is the K value going to be? Greater than 1, equal to 1, or lesser than 1? So this number on top is bigger, this number on the bottom is smaller, so big over small, K value is what? Greater than 1. So this is greater than 1. So K is greater than 1. That is a fact. You should have written that down probably from last night as well. You see that's on the first flap, right? So the K values themselves, they're called the equilibrium constant, but they have a value, a number associated with them. If that value is greater than 1, like I showed you from that graph, by the knowledge that products were favored, that just simply means the forward reaction is more favorable than the reverse reaction. It's going to happen more frequently and make more amount of products than the reverse reaction makes reactants. So correlating that graph with the knowledge that products are in higher quantity, that just means that K value is greater than 1. That means the extent of the forward reaction is great. It's good. So then tell me, how will the graph look if reactants were favored? Syrian? So hold on, do the reactants have to start at 0? Let's start off the same. I want to show you how diverse it is, okay? So what was starting down here in that previous example? Okay, so products are going to be produced over the course of a reaction, right? So they're going to start going up. Well, what's going down? Let's start the reaction still high again, okay? We're way up here. They're going to start being consumed, so they're going down. Okay, products are going up. Tell me eventually it's going to happen. Are they going to cross? And just never cross? So I did not let them cross. So who's still on top? Reactants are still on top. So who's in greater quantity at equilibrium? The reactants. So these were the reactants, this purple right here. And these were the products down here. So who's in greater quantity? The reactants. So when I plug in a K expression, as I can always do, it's always product concentration over reactant concentration. Of course, with designated numbers, I can plug them in here, and I'll do an example with this in a couple minutes. In the end, products are greater or lesser? Lesser. So you're going to be actually thinking about how a lower number on top non-colored stuff doesn't come up very well. A low number on top over a high number on the bottom. How does that make the calculation of K work out? Say again? Low over high, less than 1. So you now have a list of facts about each style. When the graphs cross, K is what? Greater than 1. Those graphs crossing, you're seeing the products have risen. It's kind of gone higher. And then when the graphs don't cross and the reactants and products kind of slim together and go parallel, that means the reactants are favored. K value is less than 1. What does that mean about the forward reaction? Is it happening and making a lot of products? No, but what could be making a lot of components or a lot of things? The reverse reaction, right? Because you can go both ways here. All right, so I've given you guys a bit of there. So you guys have these already done. What are the units of K? It doesn't have units, right? It is a number. It is not a measurement. It is a number that gives you like information about the extent of the forward reaction. It does not have a unit at all. Yay, no units. Okay. So what you'll notice is, there's a lot of reactions out in the world, right? We've got solution-based reactions. We've got gaseous-based reactions. We've got acid and base reactions. We've got a lot of reactions. So we sometimes designate just a little letter next to K to say, hey, this is the style of reaction I'm talking about. Let's move on from there. So there's KCs, KPs, KSPs, KAs, and KBs. Those are all just equilibrium constants. They're all set up exactly the same way that Zach told you, C times D over A times B. But you have to be able to plug those into the correct style of question. That's it. It's just tomato, tomato. They're all exactly the same thing. It's just we want to make sure we know what kind of reactions we're referring to. So I'm going to start with KC, and we'll make sure we know what to exclude from the K expression. So we're on the second little flap now. So here we go. I have given you guys this paper. It's not this? It might be a little small. So turn it over till you see the part where it says Chemistry Chapter 18, Worksheet 1. So we're going to do that in just 1 second. Okay, so find that for me first. And I'm going to show you this first. Okay, great. So this is that information that we were just pulling the reaction from. This is your fact about what to never include in a K expression. If anything is a pure solid, meaning it has S next to the element or the symbol, or an L for liquid, those are basically unchanging concentrations. A solid itself doesn't have a molarity. Like what's the definition of molarity? Moles over liters. Well, if I'm a solid, I'm not really a liter of anything. So because a solid is a pure solid, it doesn't have a part of a whole, it's one entity, and pure liquid as well, it doesn't have a part of a whole, it is consistently one entity. Anytime we have pure solids, pure liquids, we exclude them, and we do not write them in our K expression at all. So if D right here was a pure liquid, I would exclude it from how I wrote it in the expression. So when we write our ratio of concentration of products or reactants, we have to be aware of what can be included and what cannot be included. So here we have aqueous, aqueous, aqueous. Can I include everything, or should I exclude something? We're good to put it all in there, okay? So using this one, we are just going to write the expression. Ready? I'm going to write it down here. So I have to do products concentration over reactant concentration. So here's my product. What are my products? Put Kc is equal to, what's my product? What's my product? There's two of them. Hydrogen ion, so concentration of hydrogen ion times concentration of fluorine ion. Both of those are raised to the what power? To the first, right? Because there's a 1 and a 1 coefficient there, so raised to the first power. You don't have to write it. Over, so now that's product concentration over what? Hydrofluoric acid concentration. That's it. That's how you write the expression. That's just letters, no numbers are involved yet. How about B? We have gas, gas, and liquid. So I just heard something say again? Do not put it in there. We know it's still there. We know that's a part of the reaction. We can't just totally ignore it. But we just don't write it because it does not impact the value of the equilibrium constant that this expression is particularly pertaining to. So Kc is equal to what on top? That's a liquid, right? Pure liquid? So that's a pure liquid. You cannot include it. So because I can't put anything on the numerator, I just put a 1 there as a placeholder because I can't have nothing still in the numerator and put something in the denominator. So because I cannot exclude it because it's a pure liquid, I'm excluding it from the expression itself. But what about these guys? I can use them. So I'm going to put concentration of hydrogen gas, that's H2, raised to the second power, right, because that's a 2 coefficient, and then oxygen, so I'm multiplying by oxygen's concentration raised to the first power. So when you're writing your expressions, it's just products or reactants, excluding things that are pure solids and pure liquids. Now, I don't even have a number for you here, so we don't have the ability to even calculate the K values themselves by plugging the information in. But now we do. Okay, number two. Given the fact that all of those are gases, the way the question is phrased tells you that you can plug these numbers directly into the K expression, which is the equilibrium expression, because it says at equilibrium. That's the important phrase. At equilibrium, the values or the concentrations of H2 is that, I2 is that, and HI is that. First off, write the equilibrium expression, and then second, we're going to find the value of the constant, the value of the K. How are we going to find the value of K? Just plug them in and go. Yeah, these are already at equilibrium, so we are assuming that we can plug those directly in. Here we go. What is the K expression for 2? Kc equals hydrogen or a hydroiodic acid or hydrogen iodide gas raised to the second power. So check we've used the products over H2 concentration raised to the first. Yeah, there's a 1 coefficient there, right? Yeah. Times I to the first still, because there's a 1 coefficient there. Okay. Thumbs up if you made it to equilibrium expression. That's just the non-numerical values. Now plug your values in and calculate. This is going to be where I'm going to write it down, because I know that if you plug it in the calculator, most of you guys are going to forget that squared. Because you'll be like doing these really ridiculous numbers with your own exponents, you'll forget to square. So be very cognizant of that. Use parentheses. Any takers yet? 5.42. Give me a thumbs up when you got that. Okay, so that is, and as soon as you get that in your calculator, I would make sure that you now discuss in your, this is Kc, discuss in your table, what does that number even mean? William Bell to Mr. Smith's office. Mr. Smith, principal.
Yes.
Okay, let me see if she's available to talk to her. Okay, I'm gonna call the center. Give me 5. Okay. All right, guys. What does this K value mean? What do we know about a K value that's 5? Brandon? All right, so this is K greater than 1. There's only really 2 categories. K greater than 1, K less than 1. This is greater than 1, right? So this means, say again? So more products than reactants. So products are favored, right? So which direction of the reaction is more favorable? We're making products. The forward, yes. So the forward reaction is more favored, so it's more favorable, meaning that's why the products are favored, that's why the K value is greater than 1. Because the K value is just an expression that represents the ratio of product concentration and reactant concentration. And didn't you know that before you plugged it in, basically? Which is a larger number, this number or these numbers? Look, -2, -3, -3. This is a larger number. So you could also see it that way, and then this is a verification of that. Okay? All right, how do you guys feel right now with writing K expressions? Products or reactants? And if I give you equilibrium numbers, you just plug them in. Okay? So let's look at a couple more and make sure you're feeling good still. Sorry, I'm moving through a couple of these in a different way than I was going to. I want you guys to write down the K expression for 4, 5, and 6. Write those down someplace. It can be in your folder on that same section we've been working on, the KC one. Because that's the reaction. Write the K expressions for 4, 5, and 6 on someplace, maybe in your second plot of the folder. I'll show you where this is under there. Well, take it. Trying to give you guys time to absorb, so thank you for helping each other out. Take one more minute. This, I'm just saying this under KC. I'm going to give you guys more examples for the rest. Okay? If you already got some under KC, then write on paper. The expression. Yeah, expression. All right, Frank, what you got for number 4 in terms of the expression?
I put 1 over.
Okay, so KC equals 1 over. Why? Hold on, pause. Why are we doing 1?
Because there's all of them.
But what are we putting on the numerator?
The products. So the other way.
Okay. So guys, okay, ready? Frank's got this now. Ready?
Okay. So brackets around NG.
2 plus.
2 plus, yeah. Times BR.
Beautiful. You can put that over 1 if you would like to to represent the thought of the solid, right? The solids are pure solids, we don't include them. Or, I think it kind of looks exactly like that, so I'm just going to not put anything in the denominator whatsoever. It's cool. It's just over 1. It doesn't change the expression at all if you put over 1 or don't put over 1. But this is our expression. It's just these products because the solid over there is not able to be included. You good? Yes? Possibly? Excluding pure solids. We're just writing expression. Irie, go for the next one. Okay, KC equals. Tell me first, are we writing products or what are we putting on numerator? The flow is always products over reactants, okay? And then what do we have to include? Or I'm sorry, what do we have to exclude? So yours is what? What form of matter is that? KC is 1. I made you guys do this because you're going to forget to look at the states of matter every time unless it kind of hits you like, oh yeah, I can't do that. Oh, I can't do that one either, right? So in this one, you couldn't include anything. In this case, this equilibrium is equally favorable in the forward and reverse direction, which is why it is 1, because that's the only way you'll get an equal ratio of products versus reactants. All right, last one. Brandon, what are you putting on top? Tell it for me.
Okay.
Yes, I'm
Hydronium and
Yes.
C2H2O2.
Yes. Didn't quite hear you. What'd you say?
Okay, I put hydronium on top.
Hydronium concentration. Uh-huh.
And the
Question mark? Acetate. Okay? Confident. Over the acetic acid. Okay? Anything else? Why not water? Pure liquid, right. Pure solids and pure liquids we exclude. Alright, so whenever you're thinking about it, that's all you gotta think about. The rule of thumb is products and reactants, making sure you're thinking about how to include, these are all 1 coefficient, so these will all have 1 exponents. But like up here with Frank's example, he had a 2. Where does this 2 come from right here? Coefficient of the bromine, or the bromide. So do think about that, and then always double check, like, am I including solids or should I not be? So those are kind of the more difficult ones. So I actually gave you I actually gave you an example of a KSP, a KC, and a KA. And it's because of the style of reactions these are. If you're looking at this versus a reaction up here, what's really happening? I have a solid, and what's happening to it? It's, what's the word for breaking apart? Decomposition is something totally different. This is solid, and we're assuming, you see aqueous and aqueous, so what are we assuming that's being put into solution, so like probably into aqueous solution, right, water. And what's happening to the ionic compound? It's dissolving and ionizing, right? So that's a product, or those products are indicative of a ionization process, which it's called solubility product. It's just what is coming from the solubility of this solid right here. And this down here, this is an example of a strong or weak acid. Loud and proud. Weak acid. And this weak acid is intermingling with water, and what's happening? So this is acting as a bad acid, right? Okay, so it's donating its H+, and it's making and leaving over acetate. So we just have a basic, or I won't say basic, we have an acidic reaction, but we have a reaction happening where the H+ is just being donated. It's just an acid-based process. And so this is actually called Ka because it's resembling something about an acid. So we just changed this little subscript down here to indicate just some sort of characteristic about the reaction. That's it. So I'm going to do a couple examples like that. How are you guys doing? Because I have a lot of information for you today. So just make sure you're okay. Give me 1 to 10, how are you doing right now? 10's like, I'm super awesome cool. I know it's Friday. So you should already get a 5. Hey, sorry. Okay, spring break. You have to talk to me about what you're doing on Memorial Day. Go.
Not to get homework. That's Hey, what did it say after Megan, they messed up my freaking water. I wake up at 2 damn minutes early. And I woke up 20
All right, guys, and back to me. All right, so I'm gonna do making sure you're comfortable with the plugging in process. Back with me. That means you're back in your seat. Thank you. There is let's do 2 of these where it says equilibrium lecture notes. This actually is different. I might do these a little bit later with you guys. So on the first one it says in a gaseous equilibrium 2A plus B equilibrates to C. Do you see what I'm talking about? Okay. I want you guys to do number 1, and then I want you to do number 2. Let's start with that. Step 1. Every single time you have an equilibrium reaction, always write the expression for that given reaction. Always. Then start plugging in things. Don't try to just start plugging things in because you'll get lost. Write your expression first. Frank, what you doing, honey? I figured that's what they were doing. One and 2. So it's a style of thinking. Well, you did your part 2 of I'm just telling you, because you're going to forget to square something. I know it. It's happening. Give me a second. if you're putting your calculator wrong, you need to probably try over in a different way. Don't keep trying the same things not working. Yeah. Raise your hand if you got a number that starts with a 1. And then what's the next number? I got a 5 next. Give me a thumbs up if you made it to 1,000 and some change. All right, that means that you put in your calculator correctly. The rest of you, what'd you do?
There's a little square thing, and then I put double for your double parentheses. So I put mine times 10 for negative 2.
Okay, I would encourage you, pause. I would encourage you just to do the numerator separately, just to do the denominator, and then divide them if you can't. Because on those little blue calculators, I call them the evil blue calculators, you can't see everything. You can't see all your parentheses, it's hard to kind of keep track. So make sure you are aware that this is the answer. If you need a troubleshoot on how to put in calculator, that's on you. Yeah. You have to use the evil ones, yeah. But the math is easier, okay? All right, everybody with me. What does this mean? K value greater than 1. What does it mean? Products are favored. What does the graph look like? The graph looks like what? Who goes on top? Oh, reactants go down. Okay. Products go up and cross. Okay, and then which process is the most favorable? The forward or the reverse? Forward is favored. Okay. Woo. All right. Let's make sure we're good on number 2, and then we're moving on to the last concept. Basically, almost. Maybe cautiously, did I say that? Okay. Dose. How did you set up Q? What is the expression? Meredith. Okay, KC is equal to, I'll get you started.
I'm okay, I'm sorry. Product of reaction CH.
So methanol to the first power over
CO.
H2 squared. Okay, and it tells us actually some great information. It says the equilibrium constant at 400 Kelvin. Nobody cares about the temperature. The temperature is just a customary piece of information that's always given to you with equilibrium. But it's equal to what? Okay, and now that you know the equilibrium constant, you already know the products are favored. You kind of know some extra information. But now we have information about methanol and carbon monoxide, and the question is no longer what's K, it's what? What is H2 right here? So we will solve for that doing some math, okay? So methanol is 0.818 molar over 1.402 molar, right? And I'm not even putting molar down because K is unitless, so I'm not even going to put my units in this part right here. What am I going to put in here for H? I'll just put an X there, okay, I'm good with that. Squared, don't forget that, because that's why I make you write your expression first, because once you've written squared, it's hard to forget to write it again. 1609. All right, guys, how do I solve for X? Multiply what? What about X? You gotta pull the X out of the denominator, right? You can't really solve. So multiply both sides by this denominator?
Yes.
Okay, so putting, well, yeah, can I just pull the X out? Just the X, X squared. So if I multiply this side by X squared and this side by X squared, this cancels over here. And this stays. All right, now, what do I do? Divide by 1.609 and take that and additionally divide by 1.609. Okay. And then we will at the end. So figure out what this divide by this is if you want to first. What'd you guys get? Point, 0.58. Okay, and then divide again by the points, 1.609. So 0.36, 26-ish, 28. That's equal to what? X squared. Because this has been divided and stuff. So how do I get x now? Square root. Okay. I'm gonna get, what is it, Ishmael? 0.602. Oh, darn it. Okay, I've messed up, so I'm deleting you. 0.06. Looks good. Okay, molar, and that's the concentration of H2. 0.602. It's just an algebra, not even algebra expression, it's division and multiplication, square root, math. Okay, now I'm going to show you an expression for each of the K's that kind of delineate special situations, and I have some descriptions to go along with them. And these are just more styles of the same process, it's just more specific in terms of the specialization that we would use. So this, just the homogeneous and heterogeneous, this is just telling you can have reactions that are all the same state or not the same state. We knew that. You can put solids and liquids together, you can all gases together, they will react. So we already did kind of the KC. KP, P stands for pressure, okay? So under the KP segment, what all is supposed to be there? What's the question? Write down a type of, or a sample reaction, and what else? What did you exclude from the expression if needed, okay? Now, the P here stands for pressure. It actually stands for partial pressure. So what we do is we include only the gases. The gases are, it's a homogeneous entire reaction, so everything is a gas. So if you want to write that down in KP, everything's a gas. But the things that we're looking at is no longer brackets meaning concentration or molarity, we're looking at pressure. So partial pressure are the units that would kind of be given to you. They would be given to you probably in atmospheres or kilopascals or millimeters of mercury. It could be any pressure unit there. So this is the third flap on the foldable. Okay, so we're just going to note that it's just a pressure situation with all gases. And let's talk about the formation of ammonia as the example you can put there. You are filling out the foldable with me, yes? Okay, what is ammonia? NH3, and put G out there for gas. I'm forming ammonia, so let's just write this as an equilibrium reaction, so I'm putting my reversible arrows. And I'm going to tell you, I'm talking about the formation of ammonia from its elements. What are its elements? How do I write hydrogen and nitrogen? N2 and H2. Okay, balance that for me. Whenever you're ready. A 3 in front of the what? The hydrogen. Okay. 2 in front of the ammonia. And what's in front here? Just a 1. All right, so given that particular reaction, and you guys know those are diatomic. What? Gases. Gases. It might be helpful to write G's on all those to help represent that it's a gas. So we're going to set the KP expression. So because we're using partial pressures, we just have one micro detail that's slightly different. So that we write KP, and we're going to do it for this reaction over here. You guys okay? You good? Okay. So we're going to do it for this reaction over here. We're still doing products of reactants. So who's my product? Ammonia. And we still will square it because there's a 2 here, right? But the only thing that changes is you put a P instead of a bracket. Partial pressure of ammonia, parentheses, squared. That's just slightly different from the concentration brackets with the same style, products of reactants. Over the reactant. So who's my first reactant? Nitrogen. So I'm going to put P for partial pressure of nitrogen, diatomic, in parentheses. Do not put brackets. Brackets mean something different. Parentheses are just chilling. They're just there. and then we're going to multiply that by the partial pressure of hydrogen, but what else? Cubed because of the 3 on the hydrogen's coefficient. So that's how KPs look just a little different, but it's set up exactly the same format, and if you have values, you can plug them in and solve for the KP. The still the same rules apply, greater than 1, less than 1, products are favored or reactants are favored. Thumbs up if I can move on to KAs and KBs. Okay, we're going to come back to that in a second. All right, so the K, let's do the KA first and the KB second. So this is the 6th tab, I think is the KA one, right? 5th? Sorry, okay, yeah, sorry, the 5th one. So note to self, this is to write down under the KA someplace. KA, a large KA value, means it's a stronger acid. So you can imagine a smaller Ka value means weaker acid. And I'll make that make sense once we actually write down an example. Yeah. Yeah, we are still comparing with 1. Many times our values of these are actually fairly small anyway, so we will compare to 1. So ignore this bottom piece. This is our base. Let's go with just the acid first row. So this is the reaction when we're writing my expression for. HX is just is a generic way of writing acid, because what's in the front? Hydrogen ion. And what can you see I'm making in water? Hydronium. Whose definition talks about in water? Arrhenius aqueous, right? So this is an acid with water. It's making hydronium. This X gets left over with a negative charge there. So I don't have states of matter here for you on here, but I'm going to write it now. So this is an aqueous acid. Most of the time, acids are still diluted with water. Water is a liquid, pure liquid. Hydronium is aqueous because it's just mixed with water, and as is the other ion that is made. It's aqueous. It's mixed with water. And okay. All right, so assuming all that's true, now how would I write this expression, this Ka expression? Same style. Shout it out. Products or reactants, I heard that. And these are concentration brackets again. The only time we ever take away the concentration brackets are if we're using partial pressures. That's it. So we'll do, okay, hydronium ion concentration, because that's my product, multiplied by the other product. These are all raised to the what power? 1. Okay, so that's X minus, divided by what? HX. Why not water? It's a pure liquid. We exclude pure liquids always. Doesn't matter the type of reaction. Yeah. Good. So this Ka just looks like a Kc, right? Why am I calling this A? Because we're dealing with acids, and that's it. If we're dealing with acids, we call it a Ka. If we're dealing with bases, we call it a Kb. A Kc is just like the most generic thing you could say. Kp is just like, oh, I got gases, I got to deal with partial pressures, let me deal with this up front. Those little letters just tell you the characteristic of the reaction. There's really no more to it than that. Okay, and then, while I'm here with this Ka, what is the characteristic about strong acids that's so important to just remember? Like, basically the definition of strong. Strong means a high or 100% what? Ionization. So, say I'm a strong acid, right? And I'm, doing my ionization. My HX is my example of a strong acid, and it gets ionized 100%. So how am I writing the arrow? Forward, right, one way, not double-headed arrows like this. And I'm making HX, or H plus X minus. How many reactants do I have left here? None. 0. How many products do I have over here? 100%. So when I plug that into a K value, which if I were to plug it in over here, I would have all products and 0 reactants, right? Can I divide by 0? So basically it's infinity, right? Isn't it infinite when you divide by 0? and you can't divide by 0, but you basically have you have 100% product. So whatever the numbers were that you'd be plugging in, it would be a number greater than 1, because it can't be less than 1, because you're making whatever, like let's say you had 0.2 molar making 0.2 molar and 0.2 molar. It's always going to be greater than 1. So that's what we say a larger K value means it's a stronger acid because it's ionizing more. If it's a low value, that means you have predominantly most of your reactant left over. Did it ionize? No, I could have 99% of my reactant, which is my HX, left, and it never ionized, meaning it was a really weak acid. So there is some background knowledge there, but it's a little bit more advanced. Okay. Same thing, different story. KB. Let's write B as a base, as in B1 minus. We can write that as an example of a base. We're just writing generic forms right now. What's this base doing with water? There's two things happening, right? Yeah, water's acting as the acid, so it's donating an H plus to the B to make HB. And what's being formed? Hydroxide. So those are a couple indicators that tell you that that thing is a base and it's acting as a base. So I'll tell you up front, this is aqueous, water is pure liquid, hydroxide is also an ion, so it's aqueous, and most of the time our bases are mixed with water, so it's aqueous. Everything's aqueous except for water. KB equals whatever what? Same flow. Products of reactants. What's the first product? Hydroxide ion times HB, just our generic form of a base, or a conjugate acid actually in this case, and all over B minus, which is just our general form of a base. I'm excluding water because it's a pure liquid. If this KB is large, what can you imagine? It's a stronger base, and if the KB is small, it's more leaning towards a weaker base because of its not really high potential for ionization. Questions? What's considered like large or small? Usually greater than 1 is large and less than 1 is small. But you can still do a relative comparison. Okay, one more thing, and then I think I've gotten all your brain cells I need for today. Give me a thumbs up when I can move on. Alright, so, actually, I gotta do KSP. I didn't do this one with you. Write down this definition of KSP before I move on to the example. These are so organized. Your little booklets are they help compartmentalize it in the brain, so sometimes I like to have the flaps separate. KSP. You guys can write down that example in there. You guys know how to do this expression at this point. Yes. I'm switching to the whiteboard because I'm pretty sure that thing just stopped working again. Alright, so solubility product only, so KSP, SP means solubility product. So if you want to write down what the SP means, solubility product. What does SP mean? Okay, so it's the product, meaning this ion times this ion, like mathematical product is multiplied together, right, up to solubility. Well, when things are soluble, many times they ionize, and that's what we're showing. We're showing the solid making ions. So that's why it's called SP for solubility product. So for that example, guys, what did you write down as your KSP expression? X plus, right, times all over, say again? Do I have to put it over anything? No, it's all over one because solids and liquids are excluded. I'm not even going to write it. Actually, on AP exam, you can't write it if they think that you think something depends on it. So they on AP exam, you can't write the line for some stupid reason. Anyway, all right, so I'm going to tell you that we will practice some more of these, especially more advanced processes of solving them on Monday, along with some Le Chatelier principle stuff. Now, where was Le Chatelier's on your web part 3? Part 2, yes. Somebody tell me, briefly, those basic definition of Le Chatelier's principle. And I just call them Le Chat, so if you hear that, it's Le Chatelier's, French last name. What do you know about Le Chatelier's? Go for it, Bradley. It's called the equilibrium law, okay. What were some common things you saw? So there are all these factors that could play in that could stress the reaction. Okay, what else?
More pressure around to the left side of the equation than the right side of the hydrogen.
And it kind of depended on the pressure in general. If you could really affect it, you actually can't. But it's a stressor, and the stressor can impact equilibrium. One more fact, yeah. Right. So you guys know how to do this. If you were like in a, relaxed state, you're calm, you're collected, and all of a sudden this stressor attacks you. Maybe it's lack of sleep or too much homework, or this person is annoying you, and you just need to get back to equilibrium, to peace. What do you do to get rid of that stress? Okay. So let's say, okay, other than cry, let's say your stress is lack of sleep. What's the only way to fix it? Get more sleep, okay? Let's say your stress is you've got annoying people around you. What do? You isolate yourself. You get rid of the annoying people. So your body kind of maintains an equilibrium balance as well. What I thought I would show you was this awesome video. This awesome video right here before I walked into this, but I can do this from paper. Okay. So before I walk into Le Chatelier's principle a bit more, let me show you this awesome video. This one's called the Haber process. It's one that you would utilize in everyday life, actually. Don't put your foldable away yet. You're getting ready to add some notes to it. I still have 7 minutes with you. Thanks. Okay, no, I'm just looking for, I know, I'm going to show you one piece of this, though. Okay, I need to point out a couple of the key concepts.
What would you say is the most important discovery made in the past few centuries? Is it the computer, the car, electricity, or maybe the discovery of the atom? I would argue that it is this chemical reaction. A nitrogen gas molecule plus 3 hydrogen gas molecules gets you 2 ammonia gas molecules. This is the Haber process of binding nitrogen molecules in the air to hydrogen molecules, or turning air into fertilizer. Without this reaction, farmers would be capable of producing enough food for only 4 billion people. Our current population is just over 7 billion people. So without the Haber process, over 3 billion people would be without food. You see, nitrogen, in the form of nitrate, NO3, is an essential nutrient for plants to survive. As crops grow, they consume the nitrogen, removing it from the soil. The nitrogen can be replenished through long natural fertilization processes like decaying animals, but humans want to grow food much faster than that. Now, here's the frustrating part. 78% of the air is composed of nitrogen, but crops can't just take nitrogen from the air because it contains very strong triple bonds, which crops cannot break. What Haber did, basically, was figure out a way to take this nitrogen in the air and put it into the ground. In 1908, the German chemist Fritz Haber developed a chemical method for utilizing the vast supply of nitrogen in the air. Haber found a method which took the nitrogen in the air and bonded it to hydrogen to form ammonia. Ammonia can then be injected into the soil, where it is quickly converted into nitrate. But if Haber's process was going to be used to feed the world, he would need to find a way to create a lot of this ammonia quickly and easily. In order to understand how Haber accomplished this feat, we need to know something about chemical equilibrium. Chemical equilibrium can be achieved when you have a reaction in a closed container. For example, Let's say you put hydrogen and nitrogen into a closed container and allow them to react. In the beginning of the experiment, we have a lot of nitrogen and hydrogen, so the formation of ammonia proceeds at a high speed. But as the hydrogen and nitrogen react and get used up, the reaction slows down because there is less nitrogen and hydrogen in the container. Eventually, the ammonia molecules reach a point where they start to decompose back into the nitrogen and hydrogen. After a while, the two...
So you said so far, the bottom down here, can you imagine what started at 0 in this example? Was it hydrogen, nitrogen, or ammonia? Ammonia is the product. So you start at 0. So the product of ammonia is being made as the reactants are being consumed. And it says it's slowing down because you can see there's slopes, so we're getting kind of more horizontal to 0 slope. And then you just said at some point the ammonia starts to revert back and reform nitrogen and hydrogen.
Reactions creating and breaking down ammonia will reach the same speed. When these speeds are equal, we say the reaction has reached equilibrium. This might sound good, but it's not, when what you want is to just create a ton of ammonia. Haber doesn't want the ammonia to break down at all, but if you simply leave the reaction in a closed container, that's what will happen. Here's where Henri Le Chatelier, a French chemist, can help. What he found was that if you take a system in equilibrium and you add something to it, like say nitrogen, the system will work to get back to equilibrium again. Le Chatelier also found that if you increase the amount of pressure on a system tries to work to return to the pressure it had. It's like being in a crowded room. The more molecules there are, the more pressure there is. If we look back at our equation, we see that on the left-hand side...
All right, so let me pause for a second. Write this on your foldable flat, and this is about as simple as Le Chatelier's can be explained. So he said, the Frenchman, Le Chatelier, came in and he said, a system at equilibrium. Right, and I'm saying it right now. Okay. So a system at equilibrium, when stressed, will always try to get back to equilibrium. So a system at equilibrium, when stressed, will always try to get back to equilibrium. The only thing that's weird is the word stress. Our stresses in life are a little different than chemical reaction stresses. What were some of those that you guys saw were stresses? You were even naming them already. Yeah, Brandon. Change in temperature is a stress. What else? Change in pressure is a stress. What else? Changing the concentration of reactants or the products is a stress. Anything else? What about, so the change here could be increasing or decreasing temperature, increasing or decreasing pressure, increasing or decreasing amount of reactants. All of those things are what pertains to that particular reaction, and that's what causes stress. Let's finish this.
There are 4 molecules on the left and just 2 on the right. So if we want the room to be less crowded and therefore have less pressure, the system will start combining nitrogen and hydrogen to make the more compact ammonia molecules. Haber realized that in order to make large amounts of ammonia, he would have to create a machine that would continually add nitrogen and hydrogen, while also increasing the pressure on the equilibrium system, which is exactly what he did. Today, ammonia is one of the most produced chemical compounds in the world. Roughly 131 million metric tons are produced a year.
All right, so do me a favor, log off your computers. I'm going to follow this up with one thing before you put your phone away. So log off for me. And my smart slide just shut down, so that's okay. The Haber process, the Haber process on the board. So I know you're putting your laptops or you're shutting them down here. Before you leave me, I want to talk about one thing. Eyes on the board? Okay, so this is an equilibrium reaction. It has now been stressed. My stress at this point is I have added reactants. Okay, I'm telling you because there's like 6 or 7 ways you can stress this. I'm adding nitrogen. Oh no, I've got too much nitrogen. How do I get rid of this nitrogen? Knowing there's only 2 options. I can make the reaction happen in a forward reaction, or I can make the reaction occur in a reverse reaction. We call that a shift right or a shift left. I have too much nitrogen. How do I get rid of it? Shift right. Why? Because as I shift right, what happens to this guy? How do I make more of this?
by using up what? The reactants. Reactants get used as products are made, right? So if you have too much of one, to use it up, you must consume it. The only way you consume it is if you react it, you get rid of it. So we're going to keep working with the stress on topic. Okay, laptop's up for me?
I mean Tuesday. Yeah. So yeah, I need 2 things from you. I'm sorry, I need part 1 and part 2 of the web quest. I'm guessing, and I'm assuming that yellow and green are done. Half of blue will be done on Tuesday. And this is the important part to listen to. Blue is so long. It is stoichiometry. I would like for you to select the half, and I hope you're listening as you're putting laptops up. Select the half that you want to do. If you get stuck on something, move on. If you say, okay, I'm fine with reactions, ratios, I need empirical formulas and molecular formulas, please do those. You can skip around and do different pieces of blue, but you must do about half of it. Because once you got half of it, you could do the whole thing. You just can take more time. I know that you could do it. So your web quests are going in the box right now. Web quests are going in the box right now. And you have now in your brain that Tuesday I'm taking yellow, green, and how much? Half of blue. And how which half? Any half. And it can be compartmentalized. Are the bells not on? Yeah. Hi guys. Staplers around. What?